In this video, we're going to take a look at more extensive sorts of ways to find zeros and also the characteristics of zeros of polynomial functions. And so we're going to use something called a rational zeros theorem to be able to find the possible rational zeros for a polynomial function. And then we're going to use those possible rational zeros to actually find the zeros of a polynomial function and also to be able to completely factor a polynomial. And then finally, we're going to take a look at Descartes' rule of signs. And Descartes' rule of signs is going to help us to be able to identify the number of positive real roots, the number of negative real roots, and then the number of complex roots of a polynomial function. One of the most helpful sorts of theorems that we can use to be able to work with these sorts of polynomial functions is called the rational zeros theorem. And the rational zero theorem says that all we really have to do is just look at the constant of a function, which is going to be p, right? So p is going to be our constant. And then we have to take a look at the leading coefficient. And if we look at these two, then what we can do is we can divide all the possible factors of p by q, and that's going to help us to be able to find all the possible rational zeros, okay? And so all we're going to do is we're going to take all the positive and negative factors of p and all the factors of q, and that's going to lead us to the possible rational zeros of a polynomial function. Now, again, notice this only works for polynomials. So later in the course, when we start looking at exponential, logarithmic, other types of transcendental functions, we're not going to be able to use this, okay? But for polynomials, it works. So let's go ahead and say that if for some reason we have a polynomial function of degree n, then the equation has n roots, okay? So that's one of the properties. So basically, if we have a third degree equation, then we have three roots. Some of them might have multiplicity greater than one. Another property is that the conjugate of a complex number, so if we have a plus bi as a root, then another root must also be a minus bi. Okay, so in other words, they exist in conjugate pairs. And also, if a minus bi is going to be a solution, that also means that a plus bi must also be a solution. Okay, so there's these conjugate pairs that are solutions to polynomial equations if one of them exists. Okay, so let's just go through first and try to find the possible rational zeros before we find any actual zeros for a polynomial function. And so we have these two polynomial functions. The first one we have here is going to be 5x cubed plus 7x squared minus 2x plus 4. And I know it doesn't ask for this, but the degree of this polynomial is 3, which means that there are 3 roots. Okay, so that's going to be a property of our polynomial function. And so we look at this and we identify p to be 4 and we identify q to be 5. The factors of 4 are 1, 2, and 4, right? But we know that we could also multiply -1 times -4 and -2 times -2. So when we list out the possible rational zeros, we need to include both the positive and the negative. Right? For q, we know that the possible zero or the possible factors are, or the factors of 5, excuse me, are 1 and 5. And again, we use a plus minus. And so all we're going to do is take all the factors of p and divide them by all the factors of q. So we have plus minus 1, plus minus 2, plus minus 4 over plus minus 1. And then we also have plus minus 1, plus minus 2, plus minus 4 over plus minus 5. Or if we simplify this, we're going to get plus minus 1, all right, since 1 over 1 is going to give us 1, plus minus 2, since 2 over 1 gives us 2, and then 4 over 1, so plus minus 4, okay? So that's all for the first set, but also we would have plus minus 1/5, so 1 over 5, plus minus 2/5, so 2 over 5, and then plus minus 4/5, okay? So these are the possible rational zeros of this polynomial function. Now notice that they're not all going to be solutions, okay, or zeros of the function. All right, so it's our job in the next set of videos to be able to find those. Now, a secondary example, we have 5x squared minus 9x to the fourth plus 6. Now, a lot of students might say that p is 6 and that q is going to be 5, but that is not correct, okay? So for p and q, now, of course, we need the plus minus. So p in this case is going to be 6, and q is actually going to be -9 because that's the coefficient of the term with highest degree. And so the factors of 6 are plus minus 1, plus minus 2, plus minus 3, and plus minus 6. Okay, so you just think of two numbers that multiply to be 6, and those are going to be your factors. So 1 times 6 and 2 times 3. Factors of 9, plus minus 1, plus minus 3, plus minus 9. And so what we're going to do is we're going to divide all of these out. Okay, so we're going to take all the p divided by q. So let's start with 1, 2, 3, and 6 and divide it by 1. Well, that just gives us plus minus 1, plus minus 2, plus minus 3, plus minus 6. Okay, so that takes care of 1. Now we're going to take 2 and divide it by all 3 of the factors of q. So that's going to be plus minus 2 when we divide by 1, plus minus 2/3, and then plus minus 2/3, or sorry, 3/3. That's going to be plus minus, excuse me, 2/9, since we're taking the 2 and dividing it by all the terms. All right. But we already have plus minus 2. Okay, so we don't need to repeat that. So we're just going to scratch that out. And then what we're going to do is we're going to take 3 and divide it by all the possible factors of q. Okay, so you can see what we're doing here. We're just taking all of them and dividing. So we get 3 divided by all these. So we would get plus minus 3, plus minus 3 over 3, and plus minus 3 over 9. Right? But we already have plus minus 3. And this just gives us plus minus 1. So we don't want that. That's a repeat since we already have that. And plus minus 3/9 is plus minus 1/3, okay, which is a new one. Okay. Finally, we're going to take 6 and we're going to divide that out by all 3 of the factors of q, and then we'll be done. All right. So we have plus minus 6 over 1, okay, which we already have because that's 6. And then we have 6 over 3, so that's going to be plus minus 6 over 3, which is 2, which we already have. And then finally, we have plus minus 6 over 9, which would be plus minus 2/3, which we already have as well. And so the possible rational zeros, we would just take the ones that are left over, and we have plus minus 1, plus minus 2, plus minus 3, plus minus 6, plus minus 2/3, plus minus 2/9, right? And plus minus 1/3. So that's our process, okay? We just go through, we identify all the possible rational zeros, and then if we have any repeats, we eliminate those, okay? All right, so hopefully that helps you to see what the possible rational zeros are going to be for a polynomial function, and then some of the tricks that might occur, okay? So it's not too difficult, it's just a little bit tedious. So in the next section, what we're going to do is we're going to use this rational zeros theorem to be able to find the possible zeros or the possible rational zeros, but also to be able to solve polynomial equations.